Today we're going to look at part two of what we started at last time, which is using a Monte Carlo Tree Search algorithm to train a policy that masters an environment. And we looked at this in a few different stages. We're basing it, the algorithm we're looking at is based on this paper, which is an extension of the work that was done for AlphaGo. This updated algorithm is more relevant to us because it has some guarantees on actually achieving policy improvement, which is always what we're trying to do in reinforcement learning. So here we're taking a step back from the multi-agent problem. We're going to thoroughly finish looking at how this algorithm works for just MDPs. And then we'll see probably in the next session, we'll look at how this can be applied to these two-player games. But for now, we're just going to look at it mastering performance in a set MDP environment. And the first step we looked at last time, we had gone through this whole scenario, which is that we have a given policy function, something that we may have just been provided or something we've trained with some other method. Here I showed an example where we trained a policy that operated on this extended tic-tac-toe problem. And we had trained a policy here that was just using a policy gradient method, a common method that's part of standard reinforcement learning techniques. We saw this is a good thing to test the search improvement on, because for this environment, the optimal performance would be 1. So this is a value that is much better than the starting performance of -1, which is basically failing in every episode, to having some success, but not spectacular success. So we looked at last time how we could take this policy and then we could use this search algorithm to improve the policy. And there were a lot of, the last session is where we went through all the details of how the search function works and the theory behind how it collects data from simulations and then uses that to get an improved policy. And then we sort of concluded last time by looking at comparing the original policy to the search policy. And this is an example where I believe, there's the search policy is important because the reason why this policy function that we trained doesn't have perfect performance is that there are parts of the environment, it'll get to a state, you can see in these initial states, it has a very clear belief about what it should do. And this sort of heat map is showing what the original policy function is. And then there's a point we get to where something happens in the environment. Now it's in a scenario here where the policy function is the probabilities are really spread out and it doesn't have a clear action selection. We can see that by using search, we can, by allocating simulations to different parts of the action space that the policy function suggests, we can then get an improved policy that is based on that search data. And here we can see this is a scenario where probably this policy would lose. And now, because of applying the search to it, we can now, this ends up being successful, where it wins. This happens to be a 4 in a row connect, like a tic-tac-toe game where the win condition is 4 in a row. So this is what we looked at last time, and then we can see that this was the performance of the original policy that we trained with the actor-critic method, and then this is showing the performance, how the performance improves if we allocate different numbers of search simulations to the search function, right? So here, there's some very small improvement if we just have 2 simulations here. But, once we go up to 20, 200, 1,000, we can see that we can really boost the performance of this existing policy, right? Just by allocating these search simulations. Now, it does, of course, take a lot longer, but the whole, the premise we're going off here is that we have some computational budget to work with at the time we're deploying this. Here are examples of how much how much slower the search policy is because it has to perform all these simulations. Yeah, so that was what we looked at last time. And if you want to look at the recording of last time, they go into all the details of that. And now we're going to look at this scenario 2, which is to actually use the fact that the search gives us a policy improvement to then try to use the search as a training tool. And this is what like the AlphaGo and AlphaZero algorithms do, is they actually use the search and the improved policy you get from allocating resources to these simulations to then generate data and use that data to hopefully train a set of improved policies that just continue to get better and better. And here, because this environment, we're looking at this game against a fixed opponent. So we're in this MDP setting. The goal here would be to like master the environment, so to get like 100% win rate against this opponent. Yeah. So any questions so far about that overview? I know there's a lot of details, but again, there is a recording, but I just want to make sure we have sort of the general idea that we're using the search simulations as a way, yeah, to actually improve an existing policy. So I think before we go into all the details of how this works, I just I have sort of like a big picture overview I wrote some notes on. Hopefully this makes the picture a little clear as to where we're going to be going with this. So the initial part here showing, right, this is representing, I showed it like the heat map version of it in the notebook. Here, this is like, you could imagine we have this policy function where here I'm just plotting, like this would be the probability distribution over actions, right? So this just means like there's some high probability of this action and then a lower probability of this action. And when we do this search, we allocate these simulations. And then at the end of all the simulations, we have data from, going through the environment. We do use this policy as a way to guide the search. And then we get this new policy that is derived from the search data. And this, the convention I'm using here, so I'm calling this like pi prime. And this should be an improved policy. So the idea is like, as we go through, we can perform this search at every state, the environment, and then we can use it to get an improved policy at every state. So then we can run an episode with this where now we actually use the search policy as the policy that we allow to interact with the environment. And that's going to produce an episode like this where we start in some initial state. And then here I'm showing like we use pi prime, so the search policy, to select an action at every step. And then it results in some outcome. In this case, it'll be a win, loss, or draw with these corresponding rewards. So we basically have for every state, we have the improved policy, so here we're just using the improved policy to select an action at every step. But we also get from the search the actual policy distribution of the improved policy. And we can save that. So we have this episode, and then at every state visited in the episode, we have the improved policy, and we also have the actual reward at the end of this once it terminates, right? This whole technique, by the way, is only relevant for episodic problems. It's going to depend on this episode terminating, and then we have this reward value. So once we have an episode, we can use this episode to start building a data set. So here we have like, these are the states, and then we're going to try to train both a policy and a value function. And the policy function, we have these target improved policies. And then the value function, we're going to target it towards this reward value. So does that make sense to everyone? Okay, so we have the episode is the basis for producing a data set. So now we get into this this training pipeline we're going to use to actually do like this full policy improvement training. And the way it's going to look is that we have this replay buffer. The replay buffer is going to store information from this data collection. So we have an initial policies. I'm going to call it, I'm going to number them now. So let's say we have an initial policy function pi0. So when we run this search enhancement, we're going to basically collect data for pi0 prime, where this is like the search enhanced version of pi0. And then we're going to start filling the replay buffer with episode data from this, right? So we're going to be constantly, running these episodes with the search and then filling this data up. Then when it comes to training, we have this buffer just sitting here at all times. Then we're going to extract a batch from the buffer. So we're going to randomly sample from this buffer. We can only sample from parts of the buffer that's full. We're going to sort of assume this has like a fixed size. It'll be like a circular buffer. So data will come in, and then once we accumulate too much, the oldest data will be pushed out of it. So while we're collecting data, hopefully we're going to try to do this in parallel. We're going to collect a training batch. So that's going to consist of these states, the policy targets, the reward targets. And then we're going to use this batch just like we would do with supervised learning. We're going to do a gradient update on the policy function. We'll get to the details of what the parameters look like. But we have, the set of parameters that we're going to be continually updating during this. And when we update the parameters, now we're going to get a new policy function, which is not exactly pi0 prime, right? This is like the policy we derive from the search process, but we're going to train a new policy function on the data that this produced. So we're basically trying to match it with the enhanced policy. So hopefully it may not match exactly because this has the benefit of using the search in real time, right, in its process. But hopefully if the function is powerful enough and we're given enough training steps, we could actually mimic the effect of the search policy just with a pure function that doesn't use search itself. And then once we have the new policy, now we can start accumulating new data with the updated policy. So here, right, originally we had pi0, and then we're collecting data with this like search enhanced version of pi0. Then once we update it to pi1, now we have pi1 prime, and now the replay buffer is going to have a mixture of data, both from, exactly how much, I'll get to this in a second. It depends on how quickly we do these updates. But point is, like, we have the ability now of storing in the buffer like a sequence of policy enhancements. So does this seem good so far? Any questions about this? For the gradient updates also, this is like, we're going to train the policy function to minimize the KL divergence with these policy targets, and then we'll just minimize the squared error with a reward signal, just like you would typically do for supervised learning. Okay. And I'm sort of color coding what these generations look like. So as this process continues, the replay buffer hopefully will start looking like this, where we have, a sequence of different generations of policies where like the data in the buffer is now the enhanced version of each of these policies. Said this, so once the buffer is full, the data is replaced. So now exactly how the composition of the buffer looks like this is going to depend on a bunch of details about how these functions work, how the training works, and like the rate at which we can generate data and we train data. So just as an example, like let's say that the buffer can store 1 million examples. And then we can train at 1,000,000 examples per second. I'm just using these so we have nice round numbers. So, and then let's say we also update the generation every 1,000,000 examples trained. Now, the search rate here, I've constructed this so that this is slower, right, than the training rate. So if we conduct this whole, search process with these parameters, that means that every second we train a new generation. So we've sort of trained enough examples to cover the entire buffer, the amount, like the total amount of data we have in the buffer. And while that's occurring, 1/8 of the buffer is going to be replaced, right? Because like these stacks, like how much of the buffer we end up filling up with a new generation, it depends on how quickly we're generating this data. Right now, for the training process, we just have to do these gradient updates, pull data from the buffer. That could be a very fast process. But to actually generate data, we need to run those episodes with the tree search, right? For like every single step of the episode, we're doing the search, we're collecting data. So this process in general is going to be slower. But of course, it depends on how many resources you allocate to each part of this, right? Like if we have a lot of computers available, we can decide how many resources we're going to allocate to each part of this. And the nice thing about the search data generation is that those episodes, like while we're generating this data, we are fixing this policy, right? So we can do this in a parallel fashion. Like we can have a bunch of different computers simulating the searches and dumping data into the buffer, as long as we have a way of managing that in parallel and there's no conflicts. The training process is a little harder to parallelize. You're going to be training on a batch. Like you could, split that batch up between different computers. I mean, or just like the fact that we're training in batches, like the batching of the data itself is already doing a big chunk of the parallelism. And the likelihood is that the training rate is going to be fast enough that this won't be the limiting factor. But are there any questions so far about this, what the buffer looks like over time?
So far, I don't have any questions regarding the buffer being filled up and then that data being replaced when there's new information that comes up in that queue buffer.
Yeah. The key thing to understand here is just that, like, well, I'll get to it on the next page here, but depending on what these values are, like the training speed, the generation speed, it will change whether, there's a bunch of different generations in here or just one. And that is a sort of a judgment call. I mean, there is some sort of what I've written here where there's like this 1/8 is replaced. There is a reason for that. There is sort of a range of what intuitively makes sense would be recommended for this, but a lot of it is stuff you'd have to test just practically and see what ends up happening. Oh wait, Evelyn, do you have a question about how? Yeah, so like when we run like this, like in this example, let's say like before I update a generation, let's say I've like run the training over the entire buffer. So that would be 1,000,000 examples. That's probably not enough time for this to converge. So practically like pi 1 is probably not going to end up matching this. I mean, it should still have had enough time to make some improvement, right? But no, we don't really have a way of I mean, we can sort of see how much it's converged because we are testing the KL divergence loss. So you could actually directly see like once it has zero error with the buffer, then it's converged. But there's nothing about this process that means that you have to like run each generation the amount of training that would lead it to converge. But that is another like hyperparameter decision you have to make. There's a lot of these like hyperparameter details in this type of training that you have to worry about. So we'll see there is some like broad rules that make it work generally pretty well, but there's other things you might have to tweak for like a specific problem. But yeah, let's look at the next thing here. So there's this key ratio we have to worry about with this process, which is the ratio between the training rate and the generation rate. And then we can also, compare like compute resources we allocate to training versus generation. So these are sort of the main factors that affect these rates. So one is the mini batch size. Now, if we increase the mini batch size, we'll increase the training rate because when you do batch training, computers, GPUs, they're really efficient at doing these large matrix operations. So usually if we can pack more data into a given batch, the overall rate in examples per second will be faster. The training quality, though, might falter. Sometimes if your batches are too big, the quality of the training can be worse. And we'll see that actually practically we usually want to make the batch size smaller to slow down the training so that because again, we're going to be more limited by the ability of generating search data. Then obviously for both the training and the generation, the more compute we allocate to each one, it'll increase the rate. And then we have the decision of when we're doing the search enhancement, when we're generating the data, how many simulations do we allocate during the search? And the more simulations we have, the slower the generation rate is going to be. Now, in the extreme case, if we just do one simulation, that's not going to produce any enhancement. Like that should just match the performance of the policy. So this technique, luckily, can even have some success with just 2 simulations, right? That would be like the bare minimum of what might produce an improvement. But usually we want to, use a lot more simulations. But, I showed you in the notebook before how like using like 1,000 simulations for the policy we had, it boosted the performance from like 0.5 to 0.8 or something. That's a huge improvement. But, we are planning to train this over a period of time. So we don't necessarily have to jump straight to the end in one step because we're also really limited in how quickly we can produce that data if the simulation count is really high. So now this ratio is going to determine the number of generations in the buffer. So on the previous page, it was like, right, we had a ratio of, it was 8, like the training rate was 8 times faster than the generation rate. So that means that the buffer would contain 8 generations of policy data. And then each new generation is actually going to be trained on samples from the entire buffer. So like, let's say we're on training generation 10. So then this is what the buffer is going to roughly look like. It's going to have data from these, 2 to 9. So that means that pi 9, like there's like a 7/8 data overlap. So it's not like when we train a new generation, it's entirely on new data. This process is going to be slower, but there's also a chance it could be more robust if we have a variety of generations in here. This is probably more of an importance when you're doing this in a multi-agent scenario, because here, every one of these, hopefully, the higher the number, the better the better the performance for that policy. But again, we can test what this ratio is, and then we know how much of this data the overlap is between different generations. So also what this ratio controls is how many times a training example is used before it's replaced, right? So if this is 8, that means that on average, because of, it's going to take, like you can look at the amount of time it takes for an example to enter the buffer and leave the buffer, it will probably have been sampled. We'd expect it to have been sampled like 8 times in that. So it means for all the data we generate, we train on it, we at least 8 times or 8 steps of training before it gets thrown out. Now, in the extreme case, like let's say this value, this ratio, is much greater than 1. So here, like we had a value of 8. Let's say it's like 100 or 1,000 or something. In that case, there is more of a risk of overfitting because this replay buffer, if it has 1 million examples, that is a lot of data, but it's not that much data. It's certainly not so much that like if we were to train on that thousands of times, this network is going to be overfit to this training data, right? Because like we have in theory, we have an unlimited amount of training data, but practically, if we run this with a really high ratio, we're not really taking advantage of all of our training data. Like we're overtraining too much on the data we already have. And then similarly, if this ratio is less than 1, which is something we probably never want to do, that would mean that there's actually some training data we generate in here that never gets trained on, right? Because it will have exited the buffer prior to the training pace keeping up with it. And that's definitely not something we'd ever want. There's no point in generating training data that goes unused. So this is where, we kind of arrive at some sort of rule of thumb where, okay, we definitely want the ratio greater than 1. It could be exactly 1, right? Exactly 1 would mean that we make the least possible use of each data example. We just train on it one time until it's replaced. A value around 5, 6, 7, 8. I mean, these seem to be reasonable values. But again, there's not less than 1 we can say is bad because we're wasting resources. But anything greater than 1, it's hard to say exactly where the point is where you start worrying about overtraining. But yeah, it seems like I use this example value of 8 because this seems like at least in the range of recommended values for this process. And I think that's all I have for these notes here. This slide. So any questions about all that whole discussion?
I didn't really have any question, between the training ratio, the ratio between the training and generation. There's the heuristic of between overfitting and then wasting training data that's being filled in the replay buffer.
Yeah, like how many epics to train on? So yeah, I mean, again, like that's another thing where I would say thinking about it in terms of epics is less relevant than thinking about it like you can sort of control that by the size of the replay buffer. So if we had a pretty small replay buffer, this whole ratio and the number of generations only depends on like this ratio will cause this effect and like the percentage of the data and how many generations that will be true regardless of the size of the replay buffer. So you could say, well, for each generation, we're going to train on the whole buffer, but you could make the buffer 10,000, 100,000, a million. The larger the buffer, the longer the time will be for each generation. But it won't change these ratios. So I'd say like if you're training something and you see it's not really improving and you think that each generation needs to train longer, you could train over the same buffer. Like you could say we're going to go through like 2 cycles of the buffer or more, or you could make the buffer larger so that it takes longer to get through it. We probably do want to at least cover the whole buffer for each generation because, it is available, but that is another thing you could alter is you could, only train on half of the buffer. I mean, the nice thing about this ratio is that however long, whenever the point is that you decide to like switch to a new generation, it won't affect this information about like the average, like the number of times that an example was trained on. That's like, that only depends on the ratio. So here, we can get now back into the actual like, concrete example of this. So here now we're going to look at some code and how this works on this, specific example that we're looking at. So here, this is what I talked about where we generate an episode, right? And this is an example of like this episode data that we would get from the search function, right? So we have like, this is a single episode. It lasted 11 steps. We have the states here. I didn't mention it in the notes, but we do have these, we're going to convert these states to feature vectors because this is what the actual like neural networks are going to take as input. And then we have the policy targets we see for each step here, right? These policy targets are probability distributions over the 64 actions that exist in this problem, right? So we can see what these distributions look like. And then we have like the value targets here for a given episode. And this is an undiscounted problem. These are all going to match to be the same value. So this means this was an episode that was 1. So the reward value is 1. So here's an example of like collecting one episode's worth of data. So now what we'd like to do, what this whole thing depends on, is that we can collect data in parallel, right, while we're training it. And we also need to have a sense of like how, what the data generation rate is. So here I have this setup function, which I can show down below what it actually looks like. But this setup, we're setting up on this is the MDP that we're looking at, that, extended tic-tac-toe problem. We have the feature vector. So this setup, I have this fixed architecture I'm using. So there's like 2 hidden layers, 64 neurons each. Here for this is just like a test thing. We're not actually going to use this for the training later. But here, the buffer size is just 100,000. This is the batch size. And then these are some arguments for what the default search values are. We can change these whenever we want if we run a particular thing. But yeah, this you don't have to worry too much about this. This is just there is a problem with this algorithm where sometimes if the value, like these neural network functions, like the value function, it produces like real numbers. It could be any value, right? If we know ahead of time that we have a minimum and maximum reward, then when the search uses the value function as part of the evaluation, it shouldn't actually take values seriously that are outside of this range. Because then you can actually have a scenario where there's a winning move, which will produce a reward of 1, right? But let's say that there's another state it looks at. And the value function says, hey, this state has a value of like 2, which is nonsensical, right? You can have a value of 2. But our value function, if we have an unrestricted value function, it could say that. And we don't want, that is very bad information because obviously there is a maximum cap on the reward here. So this can help. Sometimes you get like really weird, bad performance that doesn't make any sense. And the problem is that you haven't like set limits on these reward values. So here, before I show how this setup function works, let me just show an example of what it can do. We can see this setup produces a bunch of things. And these things are all tools that we want to use for this training pipeline, right? So one, we have this generate data function, this accumulate data function. And the difference here is that these functions are things that we're going to try to use to collect data in parallel. And we need to sort of define how we want the parallel collection to go, how many resources we want to allocate to that. We have these things to update generations. This is like where we take the trained parameters and then we produce like a new, we update what we're actually using for the search function based on the training parameters. Because the whole idea is we're continually training the set of parameters that are hopefully improving. And then periodically, we take those trained parameters and we copy them into the function we're using to do the search and the data generation. And then we have ways of evaluating the performance in the environment. So these are all just like a lot of different utility functions. So this does, if I run generate data, what this function does is it just produces 1 episode's worth of data. And by default, this just starts out with a set of random parameters for the functions that we're using. We also have the option of passing a function, this PyDis. This is the function that's actually going to be used by the MCTS. So when we call this, it's going to take whatever the current, whatever this function looks like currently, whatever parameters it's pointing to, and it's going to generate 1 episode's worth of data. So here, this looks the same as what I showed before. We have the feature vectors, the policy targets, and the value targets. Now, as part of this setup, we also have these buffers. So this is where the data that we're going to eventually pull from. So we have a buffer of states, feature vectors. It matches the data that's produced here, right? And these are all circular buffers. They're empty when you initialize this. So now, if we accumulate data, so this will produce the actual data from the episode. This accumulate data function will actually generate the data, while it would also fill it into the buffer. So what this means is that we're going to, generate 10 episodes worth of data from the search. And then, oh yeah, so there's actually a number of steps and a number of episodes. There's 2 max points. So this means generate 10 episodes, and I don't care about how many steps it takes. This problem luckily has a hard cap on the number of steps each episode can be. So you don't have to worry about it. So then this is what the buffer now looks like after doing that. Right, so now it has, right, 48 thing. This is just a function of how long each of these 10 episodes took, about 4.8 steps on average. And we can see, I guess these were all, yeah, we can see how these are from different episodes because some are wins, some are losses sprinkled in. Yeah. Okay. So here, wait, did this just, okay. I thought I had a certain amount of data in the buffer. Now it looks like there's more. I may have, okay. Don't worry about that for now. So there's also a function here that does this data accumulation, but in parallel. So this is doing the same thing, but across 10 different threads. Okay. So this computer has whatever, it has more than 10 threads. But if I allocate 10 threads to this, we can see how long this took to run, like 34 milliseconds. And this only took 9 milliseconds if we allocate this number of threads. So that is the data generation side of it. Next, we're going to look at then the training side of it, which involves pulling data out of the replay buffer and doing the gradient update. But maybe first I should show how this function works. So this is the setup function. And we can see here, right, these are the arguments I passed into it that are the requirements for this. We have to define what neural network architecture we're using, the size of the buffer. We also have to define the batch size ahead of time because this is going to set up functions that pull from the buffer, produce mini batches. And to be efficient, I'm going to pre-allocate a lot of this stuff. Like there are the input-output matrices that the training is going to use. And those depend on the batch size. This is just the way I set it up now. That I could change this so that there's like a secondary setup function where you can change the batch size. But for now, it's fixed. And then these are the things that are allocated initially by default. So there's actually a policy and a value function needed. But we start out by just initializing. These are the parameters that we're going to eventually train. And then this is like sort of the first generation or generation 0, where we just copy these as the search parameters. The search parameters are what we're going to pass to the tree search, so that these are the parameters they're going to use to actually generate the training data. And then we have, these are some things to like, as part of this, when we update a generation, we want to evaluate it in the environment. So this is controlling how many, when we evaluate a policy, we can choose to either evaluate the policy function on its own, or we can try to enhance it with the search, right? We sort of have like different levels of what the policy performance is. We can say, how does this policy perform on its own? How does it perform with 10 simulations, 20, 40? So yeah, that by default, we can define like how many we want to use by default. If we set this to 1, then it will just evaluate the policy on its own without any of the search enhancement. And then we can look at what the data generation looks like. So when we generate an episode, right, this is another setup function that basically it takes like the current distribution function, right? This is what the search uses. This is the combined policy value function that the MCTS search needs. And this will create something that we can use to run an episode. And then we get training data from one episode. Now, when we do the data accumulation here, we do the same thing, right? We generate data. For this, we generate one episode of data. And then we append it to all the keys. So the replay buffer, there's like different keys. It corresponds to the policy information, the feature vectors, the value targets. So we just sort of append this, and this append function will, because it's a circular buffer, it will naturally push out the old data when the buffer gets full. Now, yeah, another thing that is part of this setup is we have, oh yeah, so here's the buffer data. This sets up all the circular buffers. Now, because we have this simultaneous data collection and training, we do need to deal with a concurrency somehow. This is a lock, which you can use when you're dealing to avoid conflicts when you're accessing the same data. I usually don't like using locks. They can be difficult to manage. Luckily for this setup, we only need one of them, which simplifies things. And when I was benchmarking this, because the whole idea is once the training function, when it needs to pull data from the buffer, we want to make sure the buffer stays fixed while that's happening. Now, it shouldn't take very long to sample data from the buffer and copy it out. That should be extremely fast. So hopefully the amount of time the buffer is locked, meaning we can't add new data to it, should not slow things down at all. That's the goal, at least. Now, if things go badly and there's conflict and we're trying to pull data and generate data, and there's a lot of conflicts with accessing that, we could see a situation where we can generate data pretty fast when we're not doing it in parallel. Then when we try to run it in parallel and we're training in parallel, we see a big slowdown in one or the other. And we want to avoid that. So whatever method we're using of managing this, we want to test it when we're just running each piece individually, and then test it when they're running together. And if there's a big slowdown, it might mean that the method we're using is bad. So this lock here seems to work pretty well. Now, this is what I was showing in the notebook when we have these like different generations of policies. When we update a generation, what happens is that we copy this copy function. This is the thing being modified. So we copy the current training parameters into the search parameters. Then we compute the performance of the current training parameters, which are now this new generation of search parameters. And then we're maintaining this list of generations where we're going to have a list of generations of policies where we have the parameters and then we have the corresponding performance value for each one. And this way we can track as the training process goes how well it's doing. There's also this restore function. So let's say we have a new generation and we're saving these generations and we found that the performance is declining. At the end of it all, we can look back and see which generation had the best performance, and then we can restore that. So this is, it's going through the generations and it's just copying the parameters that we know had a certain performance back into the current ones. So yeah, this is the data accumulation for a certain number of episodes. So yeah, this just repeats the accumulate data for however many episodes we care about. And then it keeps track of the max steps too. If we have a step constraint, steps have gone too long, then we also can break out of it. So now here's the part that we actually need for the search. Now, actually, this might be a little easier to understand. This is doing it in parallel. So if we run this function, this entire function as a block can't be run in parallel. Like it will block whatever we're trying to do, but it will accumulate the data in parallel. like in across multiple threads. So we can use this function to benchmark like how much of an improvement in data generation rate do we get when we increase the number of threads. And this, I guess it's not too long of a function. Obviously, it's way longer than the data accumulation we had up here, right? This is just a few lines. So this is managing the multiple threads, and it's doing it with channels. So channels are a way. At least this is all in the Julia language. You can, there's a link to it in the description, but it's the language I'm using for all these notes as well. But these channels are things that are ways for multiple threads to all communicate together. So they can each like try to push data into a channel, and the channel will handle the conflicts um, between them. Basically, like if one thread is trying to add to a channel, it forces the other ones to wait until that's done. So these channels, we don't need to use locks or anything. Channels work fine, and you can see that there's no reference to the lock that I set up here. So just accumulating data in parallel, we don't have to worry about that. But there's this add data function where whatever thread we're looking at, this thread is going to generate data, an episode of data, and then it's going to put that data onto the data channel, right? So here, for however many threads we're running this, each thread is going to run this add data process until we tell it to stop. Or, if we reach this limit, like there's different ways that it can stop. But I basically check either if the stop signal is on, or if, in the middle of this loop, one of these criteria has been met, meaning we've collected enough episodes so far, or we've exceeded our step limit. So now, also, this is happening. These threads are collecting data in parallel, and then simultaneously we have this other loop. This one is running on like the main thread of our computer. Right? This is like what's going to block everything else from happening, where it takes whatever is in the data channel, and then it appends that to the replay buffer, and then it increments like how much data it's collected to check if it's reached the point where it needs to stop. Now, this process running should not conflict with this one. So ideally, we have like a certain number of threads that are generating data, and then we have this other one which is independently gathering the data. And then the reason why we don't need a lock here is that there's only one thread which is actually adding data to the buffer, right? So these things are all dumping stuff to the channel. That's fine. They can do that in parallel. But the buffer itself is only ever being updated by a single process. That's why. So this whole thing is like thread safe. There's no conflicts here. And we can use this to test, how the data generation rate is affected by the threads. I think I'll wait a second before I talk about this one. Go back to the discussion of data generation rate. So are any questions so far about data generation? So I have this set up like I mentioned. Wait, is this the thing? Oh yeah, okay. So before we talk about actually benchmarking the data generation, let's verify that the training we want to do is actually working correctly. So here what I've done, I showed you this. This is this accumulate data function. So I ran this over across 40 threads. The buffer has a size of 100,000. So here what I'm doing is I'm just going to fill up the whole buffer now. And I have passed into this setup function actually the policy function that I showed earlier that we trained that had like about like its performance was like 0.58 or something, 0.56. That was like the policy function up here that we trained with an actor critic method, traditional reinforcement learning. So we already saw in part one of this from last session that we could use the search to take this policy and produce an improved performance. Now, the whole premise of this training here, what I showed here, right, is that we should be able to, right, train like a new generation that can somehow match the policy of the search enhanced policy. So we should probably verify that that is actually happening. So here I just wrote sort of prototyped this training function on the existing buffer. So here we're not doing this full training pipeline. We just filled the replay buffer with data with some number of search simulations. So the data in this buffer is all from a single generation, a single policy, but it should match or improve the original policy performance. And here I'm training parameters that were initialized to be random. Okay, so like the actual parameters in this setup are not trained, right? And we can see that the performance here, this negative 0.99, this represents the performance of the policy that's actually using the random parameters that we initialized. And here, this is after I've basically told it to train here over 10 epochs. Each epoch is just one pass through the buffer. And here the buffer is not changing. Right? It's a fixed buffer. I've just filled it with data. And we can see here that as this training process has occurred, I have this function to train mini batch. What this does is these are the two learning rates for the policy and value function. What this function does, I can actually show it in here. Let's see, train mini batch. So and this is where you see the lock come into play. We train the mini batch. So I lock the buffer, right? And then I try to do this update input output on the replay buffer. So what this does, this update input output function here, is it looks at the replay buffer. It generates a sample of indices. So it looks at like how much data is in the buffer. Let's select, I have, based on the batch size, I know how many batch indices I need. So let's just sample some batch indices. And then it goes through the buffer and it updates the value output, the feature. So this is like updating all the data that is needed for training into these matrices that are going to be used, right? This is like the value output. The feature matrix is the input. This is the input value for the training. And then at the end, I return the input, the policy output, and the value output, right? This is just the mini batch of training data that we need. But prior to doing this input output update, right, I have to lock the buffer because now I have another parallel process simultaneously looking at the buffer. What I don't want is when I'm sampling data from the buffer, I don't want it to be changing while that's happening, which will happen unless I impose this lock on it. So this is where it's only one thing we have to manage. It seems to work pretty well. This is just a check to see that the lock actually worked correctly. And then we do the gradient update. I've defined this elsewhere, just up here, but this applies the cost function, either the KL divergence or the mean squared error, and updates the gradient, policy and value gradient, which is another thing that's pre-allocated. And then I can use that, right? Like when you're doing gradient descent training, the gradient is always the same shape as the parameters themselves. And then the gradient update is just basically like an element-wise addition update where you take whatever, the change we want to make to the parameters is some learning rate times the gradient itself, where this is then gonna, minimize the loss with the mini batch that we've sampled. So that is what the training function does here. It does all of that, it pulls the batch, and this in here we don't have to worry about it slowing anything down because the buffer is not being updated in this particular loop. But then I do the generation update, which means I record the performance after running this, right, for an epoch, right? So this, I calculate how many, batches I'm going to run, right, to actually cover the whole buffer. And I guess this also partially answers Evelyn's question, which is for this problem, like how many passes through the replay buffer do you actually need for this to converge? We can see that after like 7 passes, the performance now is actually matching the performance of the underlying policy function that we use to generate the buffer data. We can see what the training rate is here. It's quite high. I think the batch size, what is the batch size I use when I set this up? Oh, I guess it's only 16. Okay. Well, yeah. Anyway, the training rate is quite high. And at the end of this, what we've done now is we've now used this buffer data collection, and now we've done sort of the first step that we need for this whole training process, which is we've trained one new generation based on this older policy function. And we can verify here that the performance, it was already tested as part of the training loop, what the performance was over time. And we can see, oh yeah, this is like, we can see here also, these are the generations that was saved as this was run here, right? It's not just the performance, it also saves the parameters themselves in here. And it saves that this performance was calculated with one simulation. So we're just calculating the performance of the function itself, not of it being enhanced with anything. Yeah, and then we can check an episode of this. We can compare the policies, but they should be quite similar. Let me go back to it. So this on the left is showing the original policy function that we're working with. Again, like this is not a perfect policy, right? Its performance is like 0.6 or something. And we're not running very many simulations for this buffer data. But just the fact that this is now matching the performance of the original policy is showing that the training process is working, right? Like it started out with very bad performance. Actually, I think I ran this forward a second time, but yeah, this is the original progression of the performance over training. And yeah, after about this many generations, it's basically matching the performance or slightly, I think it was like 0.58 was the original policy. So this is like, a 2 to 3% improvement over the original policy. And we can see if we compare it, this is like I'm calling it the distilled policy because like we're basically taking the training data we have, and this is a way, like if someone gives you a policy function, you could use this same process to then train your own function that is just like it's sort of behavior cloning, policy distillation, whatever you want to call it. We're just using this as a tool to extract the policy. We can see that for most of these steps, right, these functions are matching, right? So we're verifying at least that our training loop is working. The divergence, matching function is working correctly. And as we get a little later on, as we get distributions that look like this, we could see even this very complicated distribution that is, the probability is not concentrated in any one place. It's still matching pretty well, right? Like these look like pretty identical policies. And so here's the original policy, had this performance. The search policy that we distilled, right? So again, like we enhance the policy to like this kind of performance in the buffer, but then this distilled policy is achieving this performance without doing the whole search process. It's contained within the parameters themselves, like it's legitimately learned whatever was produced by the search process. And then this is showing we can also then take this and enhance it again by adding like 10 simulations. But this is showing this policy, if we then run this with 10 simulations, we can boost the performance up to this value, right? Which is what's being shown here. Is we take, yeah, this setup function also produces all these functions once the training is done, where this is saying like, this is just using the policy function as is, and this is using the policy function, but with the option of allocating simulations to, enhance it like we're trying to do with the search. So any questions about the distillation, this training on an existing replay buffer. So the next step is looking at the generation rate and sort of benchmarking it. So here I have this way of measuring generation rate with different numbers of threads. This the way this function works, there's another function, it's the one I didn't show yet, but it's something where we can run it and it will start accumulating data in the background. And we can sort of check on it periodically. What this is doing is it's checking the step count, which is a real-time update of how much data it's generated. And once we reach the minimum number of examples, it stops the data collection, right? This is like, there's sort of like these different functions that modify the process. So we can start the data accumulation, we can stop it, and then we can check the data rate. And here I'm benchmarking it over different numbers of simulations. So here's just a verification this works. This is the data rate running with 16 threads and 2 simulations, right? The data rate depends on both. And here is what it looks like just benchmarking this. So we'd expect the more threads we allocate, the faster we can generate data. And the number of simulations we allocate, the slower we can generate data. We can see down here, like if we only have one thread and we're using 512 simulations per step, then we're only generating 60 examples per second. Back here, we're generating, almost 86,000 or so. So this is also verifying that our multi-threading is working well, because like we should roughly be like doubling the rate. Like if we go from 1 to 2 threads, you can see it's not going to be perfect because there's some inefficiency with the threads, but we can see this is a log-log plot. So this means that every time we double the thread count, we have a similar percentage improvement in the generation rate. Now, the training rate, similarly, we can measure. And here we're measuring it. So this was measuring the generation rate just on its own. It is running across multiple threads, but there's nothing else happening in parallel. We can also look at the training rate. Same idea. Here, it really just depends on the batch size because I've fixed the architecture, right? Like this is the 64 hidden layer network. We can see here, and again, a log-log plot. The training rate increases also sort of linearly with the batch size. This is, again, a log-log plot. We can see we can substantially increase the training rate by using larger batches, the 256, right? This is training rate with just a batch size of 1, which is the minimum we could use. And so now, if we fix the number of threads, the number of simulations, and we had the batch size here of 16, right? This setup had a fixed batch size of 16. So here we can compare the two rates, and we can then see what this looks like when we try to do it simultaneously. Now, simultaneously, we have the issue showed where we have to lock the buffer, so there could be a slowdown in the data generation. But here, it's also the only way we can really test for sure what this ratio is. So now what I'm going to try to calculate in real time is the ratio that I talked about these notes, right? Where we want to compare, once we've fixed these things, like how much compute we're allocating to each thing. We want to know what this ratio is. So this is showing what the ratio looks like with different numbers of threads and different numbers of simulations, right? And this is for the setup where we have a batch size of 16. So this dotted line is a particular target. This happens to be a value of 8. So what this means is that for target's 8, like we can see what combinations of factors will allow us to hit our target or be close to our target. So apparently, like we can use 8 threads to generate data where we have 4 simulations with the search. 4 is not very many simulations, but it's still, it's bigger than 2, so it should produce something. And then if we want to use more simulations, like if we want to increase the number of simulations, we have to allocate more compute threads to the search process. So here I'm looking at up to 32. So if you have, you could also then start adding additional computers as well. So here, this is just like within one computer. So here it's like I can go up to 32 simulations and still have a ratio of like 12. But then, I could also increase the number of threads. You could sort of estimate how many threads you would need to bring this down to 8. And then we can test this ratio. So this is testing it for 32 and 60. Yeah, 32 threads and then 64. Yeah, so this is the same. This should be the same as what I calculated up here. And yeah, so when we allocate 32 threads, a batch size of 64, we see what the ratio is here. So we have the generation rate is like 2,700 examples per second. Training rate's 87,000. The ratio of 32. And then this is the data generation rate that we would get running the same parameters, but without the training running simultaneously. We could see that, this is essentially within the noise level of these values. But so the data generation is not really being affected by the training process, which is what we want. And this ratio obviously is like probably higher than the target value we want. I also made the same plot for the 64 batch size. And we can see here that whereas here we could maybe get away with up to 32 simulations, right, with our max threads maxed out. Here, if we have this target ratio, we can probably only do like half the number of simulations, because by increasing the batch size, we've increased the training rate, right? Like I showed, like increasing batch. So if your ratio is too high, one option is to just lower the batch size, which could actually improve the quality of training, possibly, but it will also slow it down so that you don't have this problem of overtraining on too much data. So we now have an idea of what hyperparameters like this we need to make sure that we're collecting data, training it at about a reasonable pace. And now we can look at actually what the full, training pipeline is going to look like. So I already showed this a little bit in the setup, but we randomly initialize the policy value parameters. We have 2 copies, or we have the search parameters and the training parameters. The search parameters are going to be used to generate data. The train parameters are the ones that are continually being updated. We're going to save a copy of the search parameters as like an initial generation of data. Then we have a set interval we're using. It could be one pass through the buffer data or multiple passes through. But after a set interval, we're going to update the generation. And what that means is that we evaluate the performance of the training parameters in the environment. We copy them into the search parameters so that now the new data accumulation is going to be based on the most recent training parameters. And then we're going to try to keep track of which generation is best so far. And then we just repeat this process and we check performance as it goes. We could have different stop conditions. So, yeah, this is like what a single like generation update looks like. We think about the whole training loop. I have it here in more like text, and then, well, you can see the actual like code version of it. But we have to decide what our data generation rate is going to be, which means we need to figure out how many threads to use, the mini batch size, the number of simulations. These are the main levers we have to control this ratio. And then we need to also select how often we're going to generate, or how often we're going to update the generation in batches, right? So that should be like as a fraction of the buffer size. Like we have to divide the buffer size by the batch size. And that'll tell us if we're training, like if we want to train through the buffer once, this will tell us how many batches we need to train on. So then we're going to keep track of a failure count. Failure would be if we train a new generation and its performance is worse. And then we're going to loop. This is one option. You could also just loop for a set number of times, or you could do it dynamically based on if it's still improving. So we're going to loop until the failure count exceeds some threshold. So then we're going to train the parameters for this number of mini batches. And what that means is that we're going to initialize the data accumulation process. So we start accumulating data with the search parameters that are fixed from that generation. And then in parallel, we repeat n times for n mini batches. We pull the data, the buffer data, into a mini batch, and then we do the gradient update for that mini batch. We do this for the number of, the number of mini batches we've said should equal one generation. Then we check the performance of the current training parameters. We copy them into the save generation. We update the search parameters with a new generation. And then if it's improved over the previous one, we can reset the failure count to 0, right? Otherwise, we increment it by 1. So this is like simultaneous failure. So it's okay if we fail once, it'll reset. Our criteria is going to be like, did we have like 5 generations in a row that failed, right? That would be, we're not going to be so harsh as to say it has to improve every 1 generation. And then also, if we're getting failures, we can lower the learning rate. Optionally, that might be an indication that the learning rate is too high. And then after the training is complete, we have hopefully a list of parameters over time and that have improved of every generation. If there was a decline, we have saved all the steps along the way. So we have the option of resetting to a previous generation. So now we can look at doing this on this grid capture problem I set up. So here, this is setting up this training pipeline with the same problem I showed earlier. We train the policy on. Here, I'm actually setting the replay buffer to be of size 1 million, and this is the batch size of 16. And the reason why I did this is because if we test these data ratios, here we want to make sure we're doing things reasonably, right? So here I've set this up, batch size of 16. The architecture, this is the architecture again we're using. And now I have this train networks function is going to do that whole process that I described, where it's going to generate data in parallel, it's going to train the batches, and it's going to produce an output that tells us these statistics about what happened. So it tells us what was the generation rate, what was the training rate, how many examples total, the total time, and then this is the ratio. So the way I've set this up here, this is a ratio of 10, which is not 8, but it's close to 8. It means, we'll have 10 different generations in the buffer instead of 8. We'll train on any given training example an average of 10 times. So, and this is with 35 threads accumulated or allocated to the data collection. I also made this other function that allows us to test across different batch sizes. This will like redo the setup for different batches. So here, this should match, right? We're getting a ratio of about 10. These are the same parameters I used above. Batch size of 16, 35 threads. Oh yeah, also, this is with 60 simulations allocated to the search, right? So this is pretty good. Like anything above 2 is fine. The higher we can go and get away with, the better, because this will produce better data. The more simulations we can allocate. And then here I'm testing it with a batch size of 64. So, right, if I use a batch size of 64, the training rate's higher. So here, like, I had to lower the number of simulations. Here I lowered it to 30, and then we get a ratio of like about 7. So this just again highlights the problem of, like, you always have the freedom of changing the batch size, right? Here's the training rate here, like 63,000, and here it's like 80,000. So that's how much it increased from the batch size increase. So, okay. That's like, this was to test what kind of parameters we want, like how many simulations. And we can see that I copied it down here. So here I'm doing this 60 search simulations, 35 search threads. This is just to make sure I don't, I also made it so if I set a target ratio, I can actually I can pause the training if it's going too fast. This just means the training's never going to pause. But I already know this will produce a ratio of about 10. And then, yeah, this is the base learning rate I'm using, 0.1. I'm using a failure limit of 5. And this is not being used. Yeah, see, this will continue until the failure count is reached. And I'm just, each generation will be like one epoch, meaning one pass through the replay buffer. And this is just, if the generation performance, I cut the learning rate in half if the performance degrades. So I ran this previously. This thing, it took not too long. This whole thing took about 570 seconds. And we could see from the output here, initially it started with terrible performance, losing every game. And then there was some initial improvement that was pretty slow. It starts improving pretty quickly. This is just reporting the performance after every generation update. And then actually here, were there any failures here? So then, see, it keeps going. And then at this point, it starts to fail once we hit a performance that is near perfect performance, 0.975. Here we could see that it hit a cap where it could no longer improve. We can also see here the performance over the generations saved, right? This is what's being saved in the policy and value generations. See, starting here, and this it went through 30 generations before failing to improve. So this is just how it worked out. The way I set this up, buffer size 1 million, ratio of 10, like how successful this is could entirely depend on all those hyperparameters, but it'll probably work. Like you could maybe improve the number of generations this takes, tweaking the learning rate, tweaking the size of the replay buffer. But this was the case where the actor critic method, right, kind of capped out, at least the way I ran it, at like 0.56. So this at least, and that algorithm also was like having a failure count and allowing it to check and run repeatedly. And the way I set it up, hit a cap earlier. So this managed to, I would argue, basically master this environment here. You can see this is the best. And then on top of that, once we have this process done, I can also test the best policy with search on top of it. So here I'm running it with 200 simulations, and then it boosts the performance up to, basically it wins every time, right? From 0.97 to 0.99. And we can also test, so there's also a function here to extract a previous generation and then test that. What I'm doing here is testing. So the raw policy, this is the curve of just this policy generations over time. And we can see the rate of improvement here. Here I've converted it to a win rate, right? The reward is -1 to 1, but the win rate is 0 to 1. So here we could see how the win rate changed over time. It actually gets pretty close to ideal after just 15 generations, I don't even have to go out to 30. But then I can also go back and retroactively look at, if I enhance the policy with simulations, how quickly was that improving? We can see with 20 simulations, like after just, 6 generations, this policy function, when enhanced with search, was already capable of having near perfect performance. And the more simulations I add, it should be better. 10, 20, 40. We can see, the like 40, it improves pretty quickly, but we can see that the fastest, if I just add, 40 simulations is not that much. It's actually less than what I'm even using to generate the training data. But after just 7 generations, this is already at performance of basically 1. And these curves also match. There are curves like this also in the paper, this original paper here, where they track the performance of this over time. But like with the benefit of adding search, simulations. No, that might not. One of these charts in this paper, yeah, looks at adding. I believe this is looking at adding, seeing how the generations over time improve even faster when you also analyze them with simulations allocated. And then at the end, this is the policy we have here. Right, it should basically never lose. Here I'm running it actually with 200 simulations, so this really should never lose. We can see what the performance looks like with like what the policy actually looks like that it's running. But here, this is like the search enhanced policy. We can see it actually does something a little funny here, which is instead of just going for the win, I believe this scenario probably is still guaranteed to produce a win because there's too many things it's attacking. We can see that the original policy either favors making this move, which just wins immediately, or doing something that guarantees a win at a later time. Because this is undiscounted, this training, it's not actually incentivized to win quickly. So sometimes it will do something that will win, yeah, at a later time, even if it could win already. So yeah, you can see, and if I run this, like I haven't found an episode yet where this loses whatever seed I give it. It seems to produce a win. But this is also winning longer episodes, right? The previous policy would tend to lose episodes longer than like if it got blocked on any initial attempt. So here it's found that there's this weakness in the opponent here where it's very weak to forming diagonal connections. So it's bad at, this particular opponent is bad at defending these diagonal connections. So most of the wins end up forming these diagonal patterns. So that is an example of this whole training pipeline running from start to finish and showing that as an alternative really to like a traditional method, like an actor critic method, you can use this to manage the generations of policy improvement. And then also have the option when you're done of having these enhanced versions of the policy you already trained. So, any questions about this and the final learning curve of this and everything? So this concludes how you would use this to master an MDP environment. Now, the next step beyond this is applying the same technique, and everything would be almost exactly the same, but in a self-play scenario where like we have this game, but instead of mastering against a fixed opponent, we use this like the way AlphaZero trains, where it does self-play, where it's playing against itself in a two-player game, zero-sum game like this. And then hopefully what you end up with at the end of that training process is something close to like the minimax policy, which is like a policy that can't be exploited. And a lot of that process will be the same as what we looked at here with the enhanced search. There is a little bit of difference, and you have to handle the player switching with sort of multiplying some of the rewards by -1. But otherwise, everything about this is very similar. And then the other thing, which is going to also tie into the next part of the multi-agent reinforcement learning chapter, is there's this discussion of when we have here, we have an MDP environment and we can monitor just performance in that environment. When we have a two-player game and we want to know like how good is this policy, we kind of have to test it against a family of opponents, because we could best a single opponent in the past, but then that same policy could lose to a previous opponent. So this is where actually having multiple generations of opponents or policies in the buffer is important when we adapt adapt this to a self-play scenario, because we want to make sure when we test the performance that we want to test it against a family policies. And when you test or like an ELO rating or something for a game, like a 2-player game, you need to you need a population of players to test it against. So I think what we'll do next time is look at what this looks like in the true like multi-agent self-play scenario, and then try to tie that into sort of the population learning. Because I think the very end of this chapter in the multi-agent book covers population training and how to manage, and that actually ties nicely into the AlphaZero discussion. Because unlike in the MDP problem, to evaluate the effectiveness of this training process, we have to not only maintain generations of play, but take those generations and turn them into populations of opponents that we evaluate, just to make sure that we're really improving performance, right? Because we could always improve against one opponent and do worse against another, and that would be a problem. We want to sort of universally do better against any generic opponent. So I think we'll start looking at that next time. And yeah, any follow-up questions or recommendations?
Hi, Jason. My name is Anu. Quick question. I joined late, so I'm sorry if I missed that. Is this a Python notebook?
Oh, no, this is a Jupyter. I'm sorry. This is a Pluto notebook in the Julia language. If you look at the meeting description, there are links to all the resources. So there's a description of Julia language, Pluto notebook. It's what I've been, if you go back and look at previous recordings, it's the same code and notebook I've been using for all the reinforcement learning stuff.
I see. Thank you, just.
But yeah, all the code, there's a package to this that you can also find on GitHub. This you can't really see it here, but there's a reinforcement learning package that I developed when we were doing the previous meetings for reinforcement learning, and that was all. Yeah, it's all on GitHub. But that was all developed in Julia and all the notebooks. So yeah, all these interactive tools and things. The nice thing about it is you can look at all the code in one place. It's not using any sort of external RL dependencies or big like heavy packages from other places. So I think it's better for learning. If you're interested in learning about the stuff, you can sort of see everything in one place. It won't be like obfuscated behind a bunch of other packages.
I see. And I just accessed the meetup page, and then I see all the links there.
Mm-hmm. Yeah. You can also find their recording. So this session also was dependent on what we did in the previous session. I have it here, but this is what we did. So all the early part in the meeting, which you may have missed, but I was talking about how this how the search actually works. This meeting was all about sort of building the training pipeline. The previous meeting was about understanding how the search actually operates and leads to policy improvement. So you can look at the recording of the previous meeting to see that information.
See, thank you.
And yeah, there's also a link to the paper in the description, which is very helpful. All the math and the algorithm it's used in the search is based on this paper.
I see that.
Yeah. So any other questions or ideas about future meetings or the multi-agent book? I think after this population topic in the multi-agent book, I believe that is sort of the end of the academic material in that book. There are some other sections on environments and training, and yeah, we can see, but I mean, yeah, there's some other ideas I have, but this whole thing on this AlphaZero training was also a bit a diversion from the book anyway. So we're sort of padding it out a bit, but yeah, like none of this stuff is, the book has a very brief description of like AlphaZero and it doesn't include this new version of the search that is now. I would recommend using this type of method over anything that was in the original AlphaZero paper. Yeah, this method works much better for policy improvement. Okay, well, if there's no other follow-up questions, we can end for today. And yeah, hopefully next time look at these techniques applied to two-player self-play type scenarios. Good, so thanks for coming, everyone.
Thank you very much.